Hi everyone, greetings from Switzerland. I'm very happy to welcome you to this first of two webinars focusing on quantum computing, going from foundations and hardware platforms to quantum computing applications. My name is Elisa Bäumer and I will be the moderator of this webinar. I'm a PhD student in the Quantum Information Theory group at ETH Zurich and an intern in the IBM Quantum Community team at the IBM Research Zurich Lab. This webinar is hosted by Messe München and co-organized by IBM Research Europe, in view of the quantum world at the LASER World of PHOTONICS. While the World of PHOTONICS Congress will still take place online June 20th to 24th, the LASER World of PHOTONICS in Munich has been postponed to April 26th to 29th, 2022. Until then, we are hoping to facilitate knowledge exchange and communication in the industry through a new webinar series, which is live-streamed free of charge. Today, it is starting with the topic quantum computing, from foundations to state-of-the-art of hardware platforms. For this first LASER World of Photonics talks, I'm very happy to welcome our speakers, Dr. Thomas Mons, who is co-founder and CEO at Alpine Quantum Technologies, and Professor Dr. Stefan Philipp from TU Munich and Director of the Walter Meissner Institute. During the talks, you are encouraged to ask questions using the Q&A window at any time. The most relevant questions will be published, but as we might not have time to answer all of them, please make use of the upvoting questions to select your favorite ones. The most upvoted ones will then be asked by us at the end of the talk. So let me start by introducing Dr. Thomas Mons, who will give the first talk titled From Photons via Lasers to Quantum Computing. Thomas Mons finished his PhD in experimental physics at the University of Innsbruck, focusing on the realization of quantum algorithms. His achievements include the implementation of Shor's algorithm and the entanglement of 14 qubits. After a detour working for a laser company in Scotland, learning about sales and product development, he returned to Innsbruck and briefly afterwards founded AQT together with Professor Blatt and Professor Zoller. He organized the design of the first ein-trap quantum computer installed in a 19-inch rack and demonstrated 24-qubit entanglement in that device recently. So welcome, Thomas. We're looking forward to your talk.
So then. Thank you, Elisa, for the nice introduction. Well, welcome to this LASER Photonics conference webinar on quantum computing. You might wonder, like, how the heck, why would quantum computing come up at the laser show in some sense? And I'm trying to give you a little bit of an overview and motivation, on the hand of quantum computer and why is there so much buzz about it in the media. And at the same time, I'd like to point out why we, at least with trapped ions, use lasers heavily, rely on photonics, and actually for the next stages of development and scalability, we will even more heavily rely on a tight connection between our quantum computing efforts and the entire photonics world. So this first slide, what you see here is really an ordinary ion trap as developed by AQT. It's mounted on a vacuum flange and we store atoms on the inside. And the goal of my presentation is now to A, show you what are the applications, B, what's state of the art, and then towards the end of my presentation, I'll point out how this connects to many of the products that some of you in the audience might offer or services that you're pursuing. So quantum computers are set to replace or at least actually enhance the capabilities of HPC facilities. And here you see a picture of the Leibniz Rechenzentrum in Munich, which is a state-of-the-art classical computer facility which offers lots and huge amount of computational capacity. The applications range from optimizing, for instance, logistics, recommendation systems, as we, for instance, use from Amazon to Google to advertisements in your social media. There is optimization of chip layouts, as, for instance, are used by Infineon, AMS, and other entities. There's a strong connection also to the finance world when you want to do, for instance, high-speed trading, which again connects us to, for instance, fiber connection between different nodes. There is the aspect of cybersecurity and figuring out as fast as possible that something's awkward is going on in your network. On the finance side, you can also think about profit and loss, optimizing the capabilities of a portfolio, but minimizing the risk and loss. And then there are moonshot projects, for instance, material design in terms of can we develop room temperature superconductors, which I'm convinced Stefan would very much like to have room temperature superconductors, or medicine application in terms of chemistry, to figure out and reproduce processes that are going on in nature right now. For instance, talking about fertilizers or carbon binding. And to give you a feeling why these moonshot projects are so motivating, if we manage to solve high temperature superconductors as well as nitrogen binding, these two projects on their own would already reduce the global power consumption by more than 10%. And that's one of the, and that's like annually. And that's one of the big reasons why people look into quantum computing as a successor for classical computing. Well, why do I mention like a successor? Why do we need something? So there's one big problem. If you look at the speed of typical CPUs, if you look at your own laptop, for instance, the speed has not increased at all over the last 15 years. And seeing that the amount of data that we generate is still growing exponentially, but is essentially capped now, and how much computational capabilities we have, many people are concerned and are questioning like what's coming next. And if you look at HPC in particular, you will see that currently more than 60% of the applications in HPC are somehow connected to physics, to chemistry and math. And so, yeah, well, what could be one of the many plan Bs compared to classical computers? And yeah, just looking at one of my favorite old pictures is quantum computing exists. I am going to briefly talk about trapped ions as a platform for quantum computing, and Professor Stefan Philipp afterwards will give you this on the left-hand side, an overview about the superconducting efforts, where they are and what they can do. And it's not clear at this point yet which platform will win. All platforms have advantages and disadvantages, and we'll briefly go into that in the context of this presentation now. So, trapped ions, what's a trapped ion quantum computer? What does it look like? To a very large degree, this is a state-of-the-art quantum computing experiment, as you would find it in an academic setting. So this is a picture from the Academy of Sciences in Innsbruck. You see on the left. Now let me try to make this drawing thing work. Actually, I can't draw because my video is on top of the drawing tool, but yeah, whatever. On the left-hand side, you can see a vacuum chamber in this blue-violet shaded area with lots of lasers on the right-hand side, taking up most of the lab space. And then PhD students and postdocs on the left-hand side would usually operate this system. Such a device roughly takes about 50 to 70 square meters of space and is constantly monitored by students and postdocs to keep it operational. What we actually do is we have, for instance, a configuration, as you can see here. Inside a vacuum chamber, there are a couple of metal plates and tips. Two of the plates are grounded, two of the plates are connected to an RF signal, and these tips that you can see on the sides here are at high voltage. And using photoionization, we can store ions on the inside. And these ions, as you can see here, are being looked at with a camera from the side because they fluoresce when we illuminate these ions with the correct lasers. Well, how does the storage of atoms and ions actually work? So you can think about, similar to my nieces, you can think about using electrostatic forces. If there is an atom is not charged. But if it's actually charged, you can use electric forces to try to keep it on the inside. Usually these slides would have an animation showing you on the top right that in free space you can't store an ion. So it would always find a minimum in your potential and roll down that hill. However, if you're using RF, this RF is actually accumulating and averaging out to a quadratic confining potential similar to harmonic oscillator. And then this ball, which on the top animation usually would roll down, is nicely stored on the inside. And that's how we can use electric fields to store atoms and ions in space. There are many different configurations. Where we started off initially with the Paul mass filter, which received the Nobel Prize many years ago. And then this one has been adapted in design from Innsbruck with rods to blades to multi-layer traps, even to the point that nowadays semiconductor companies such as Infineon are producing the first semiconductor-based ion traps for large-scale scalability. Which ions do we usually prefer? So, well, it's the good old role of keep it simple. Most of the physicists prefer to stick to atoms in the second column. The reason behind that is that as we remove by photoionization a single electron, you'd have two outer electrons. You remove one, you essentially move to the left. You end up with an atom which has just one single outer electron and therefore has a hydrogen-like level structure. And this hydrogen-like level structure is then spectroscopically easy to manipulate, and it's a really good foundation to build qubits. These qubits, in very simple terms, can, for instance, be looked at as a V-shaped level scheme. You have a ground state, you have an excited state on the top right, which has a lifetime of seconds, and even depending on other qubits and other encoding, this lifetime can essentially be minutes, hours, and years even. And what you do too is now you use another transition to probe whether the electron is in the ground state or in the excited state. If it's in the ground state, the laser would excite the electron, you would go to the top left. The lifetime is very short, and after only a couple of nanoseconds, it would decay to the ground state again and scatter this photon into the entire 4 pi space. And that would, on a camera, because you do that millions of times per second, you would get a bright dot, as you can see on the bottom left or on the right here. Alternatively, if your electron has been excited using another laser to the D state, to the excited state, where it lives for a very long time, then obviously the electron can't be excited. Nothing gets scattered. If nothing gets scattered on the camera, it would be dark. And we have bright and dark. Well, that's what we are used to from a spectroscopy point of view. We'd have a certain label. But if you talk to an informatics computer science person, they would say, well, rather than bright and dark, why not just call it 0 and 1? 0 if it's dark, 1 if it's bright, and then you immediately have a connection towards, can we build a computer? If you want to build a computer, you have to have some means of manipulating your quantum register. Without going into the details, what we generally do is we have laser beams which illuminate the entire register. We can essentially do collective bit flips from 0 to 1, from 1 to 0, with gate fidelities notably better than 99% fidelity. On what you want and need to have in addition to build a quantum computer, you have to have means of having these qubits talk to each other. Thinking about it like that, you want to have an interaction where you would say, if the first qubit is in the excited state, then make a bit flip on the second qubit. If the first qubit is not in the excited state, say in 0, then you shouldn't do. This is what is referred to as a Z0. In our case, we can implement such a behavior using bichromatic light fields with fidelities of better than 99%. And recently, we have extended this set of tools, not just to work collectively on the registers, but we can do that now on any subsets of qubits for more than 10 to 20 ions. We want to push that now towards 50 qubits. Well, again, a computer science guy would say, I don't want to learn about lasers. I just want to have these systems controlled. The way you do that is what we in the lab or in a device would call certain interactions with different lasers would be represented by unitary operations. This is essentially a way of mathematically writing down what happens to your register. This can be on single qubits or a subset of qubits or even all of the qubits. And in addition, we have some special gate operations, which is more like for the specialists in the audience, like hiding qubits from further interactions, resetting qubits, storing them in, say, memory states, and so on. What is a key part, and that's something where I think it was really interesting to work now with IBM, because they or also with Stefan and others, is like, look, we can learn and benefit from everything that has happened in classical computing. So let's say there is some interaction, some operation, some computation that you want to implement. What you can see here is a visual representation of a computation taking place. There would be laser pulses on specific ions in specific configurations with certain lengths and phases and frequencies and everything. And you'd end up with a sequence where essentially would say there are 200 gate operations on your register. But you have seen before these fidelities, like the performance of these qubits, it's not perfect. We are at 99 something, but it's not completely without errors. And so in order to make sure that you can trust the result, what you want to have is, well, can't I use something like a compiler that I'm used to from classical computing to somehow push that together, make it smaller, have less gate operations show up, and because there are then less gates, the performance improves. Yes, these capabilities exist. So for instance, there are compilers in Qiskit, which is one of these quantum computing software development kits, which AQT, the University of Innsbruck, and many other nodes are actually connecting to work together with IBM to make sure that of any hardware that's out there, we get the utmost performance out of those systems. And here you see one of those examples where when we start off with 200 gate operations, by using different set of gates, using different compilers, this can be reduced by up to a factor of 4 and more. And you can immediately get, it's like if there is a factor of 4 less gates, then there is also a factor of 4 less probability for errors to occur. So what do these systems look like now? So we have at AQT realized qubits which are stored on the bottom left in this little black box, the entire vacuum chamber, the camera, the magnetic shielding, everything is included there. On the top left, there is essentially vacuum controller, vibration insulation, and all the lasers that we need are just these rack-mounted small modules with a couple of fibers connecting the right-hand, what we call laser rack, to the quantum computer rack, which is on the left-hand side. If the animations would work, which they can't because it's all based on PDF files, you see a register of 55 ions at the bottom, all of them being bright. And usually you would now start to see how these ions start to blink. And as they blink, you would immediately say, well, okay, bright is 1, dark is 0. Now I have an intuitive picture how quantum computing can look like with an ion trap-based quantum computer. Well, how is the system accessible? I mentioned before, IBM started very early to work on something like a quantum programming language. There is Qiskit, there Google worked on Cirq, there is PyTicket from CQC, there's Penny from Xanadu. There are a couple of quantum software platforms to build on, and you can access via the cloud several devices, not just the ones in Innsbruck or from IBM. However, what we prefer to do at the moment is really figure out what can we do with quantum computers. So we have collaboration with, for instance, Yoast and Multiverse, which are working on finance applications for quantum computers. We are working with Michael Marthaler from HQS and Benno Breuer from Quantco in the context of chemistry calculations, chemistry simulations to better understand, for instance, what happens with an oxygen molecule on a metal surface and how, like, for instance, does rust happen? Or what can you talk about, like, in terms of battery design? There are many, many fields where you can do material development with these devices. And we're currently trying to figure out what's the best way forward, given the capabilities and shortcomings of our platform. And then, for instance, Riverlane is trying to work on improved control of quantum computers to get the utmost performance out of these systems. So how does that scale? For the moment, we confidently work with 20 ions. We know our system, in principle, like in terms of control of individual ions, we can go to about 50. However, our system was initially really designed to get us to many, many, many ions. And you can see here pictures of more than 100 ions being stored in our ion trap. What we need to do and what we have to solve is how can we control all these 100 ions with laser pulses. We, for instance, are working together with the University of Innsbruck as well as with Fraunhofer in Jena on fiber integration, fiber-based addressing of these 100 ions in a very stable fashion without phase jitter and so on. If someone of you in the audience says, oh, we can do that better, I actually happen to have a module that could be a perfect fit for this challenge, please let me know. We'd happily think about how to benefit from the knowledge in the photonics audience. Well, so that brings me to photonics. So how does these systems scale? What are the challenges? And so one thing, like how we tend to group it, is like we have to scale up the systems. We need to get to more and more qubits. One way of doing that is, for instance, thinking about 2D designs. We have to get better control, and better control usually needs more stable, better lasers with a line width of below a hertz, which we currently have roughly, but even smaller would be better. We need to scale these systems down. That not just only means that our chips and our vacuum chambers and everything needs to become smaller, but we are now almost at the edge where our vacuum chamber is on the same size as the laser system. And it just feels a little awkward. It would be like you'd have your classical desktop PC and the power supply is larger than everything else. And so we want and need to work on better, smaller control hardware. And we need to make sure that we can control these pulses and everything with higher fidelity, with higher powers. So these systems should be smaller, offer more power, and have better control. And that, for instance, brings us with fiber integrated AOMs, EOMs, and so on. On the long run, similar to what we are doing now, I mean, we are not in the same space. We are using the internet. We are connecting modules. If you think about HPC, the way forward for HPC was to take copies of the same devices and figure out means of how to connect these devices. We want to do the same thing. You can immediately see that, like, look, if you are controlling atoms with laser pulses, there ought to be a way of how to hook up two different ions in two different vacuum chambers with, say, some piece of fiber. And so we are working on optical interfaces on the hardware side to really make sure we can get that going. So if you want to get a feeling of how far are we in the community, and so I'm here happily going to give you an overview of some of the research, which is not just stuff in Innsbruck, but actually also in other nodes. So when you talk, with instance, with Jonathan Holm at ETH Zurich, they have been working on fused silica-based ion traps, where they use laser weakening and etching processes to really generate ion traps on a piece of glass. And they have now pushed towards the integration of really fibers into these traps. What you can do there is you can have multi-layer traps with waveguides, where you use a grating to send the laser pulses towards the ion. And just recently, they have managed to show entangling gate operations of really, really high gate fidelities. So everything above 99% is great. This is at the level of 99.3% and can even be pushed a little bit farther. This is what they can do already right now on fiber-based integrated traps. But we have to push for instance, more fibers. We have to challenge or like tackle the challenges of how can I make turns in these traps? What are, for instance, the radius of curvature which allow us to route laser lights to these traps, to these processing centers. An alternative view, which might also be interesting for you, is think about these traps, like how can I connect not just the fiber, but how can I really connect to different systems? So Chris Bellens in Oxford, whom I'm also happy to work with, they are working on really free space connecting two ions just with a mirror. And the vision is similar to HPC. Can you build, as you can see on the right-hand side, these yellow slots always represent to a string of ions? Can you generate fiber connections, optical connection between the systems? So similar to classical computers, we build copies of these devices, we connect them via fibers, then we could generate large-scale quantum computers. Chris told me at the moment, they have 2 apparatus with 5 ions in each side, and they can work on the entire system as if they would be 10 ions. Which brings me now to the last part. You might say, well, free space is not really something you might consider scalable. So we have to get that going with fibers. If you have fibers, you immediately say, well, you might be working in the UV. How does that connect? How is that scalable? So what you see here is results from Tracy Northup and Ben Lanyon in Innsbruck. They have a similar approach to Chris. And the goal was there initially, and that's actually something I did during my master thesis, was to connect an ion to the photon and send that photon via the fiber to another node. This is one you see on the top left, something that Tracy Northup is working on. On the long run, you have to make sure that this actually is telecom compatible. So we have to figure out means of getting these blue or red photons, which are at about 800 nanometers for calcium, to convert them to 1500 nanometers. And this is something that Ben Lanyon managed to succeed at. So he did a single photon conversion from 800 nanometers to 1500 nanometers and could show that this ion photon entanglement, like the connection that you need in order to connect quantum processors over a distance of 50 kilometers, if I'm not mistaken, 50 or 60 kilometers. And so the idea now is to first demonstrate that we can build a network via a normal fiber link going through the floor and then actually around the parking lot between these 2 nodes. And then the idea is to extend these capabilities really towards telecom with repeaters. And happily, I can say that Ben Lanyon and Tracy Northup succeeded in convincing a funding agency in Austria to use the Austrian fiber network to push towards 100 kilometers and more to potentially make a connection, let's say, towards Munich or Vienna from Innsbruck using quantum communication methods here. Well, I'd like to conclude this presentation now slowly with not so much what we did, but actually point out what would I need. So I believe some of you in the audience would say, oh, I can help here and there. One thing that I very much would like to have, for instance, are fiber-based AOMs, which we usually use mainly for switching light on and off. However, a single pass configuration, as is commonly implemented, only has an extinction ratio on the order of 30 dB due to scattering. If someone in the audience has something which is on the order of 60 dB, please let me know. I know that we, plus our colleagues in the community, we probably easily order a few hundred of those pieces right away. What we also need to work on now, you saw we are relying heavily on lasers. We have to have means of having these lasers installed and run 24/7, which includes mode hopping, one of the reasons usually being air pressure changes. This needs to be gone. For plug and play, we very much want to have polarization maintaining single mode fibers, and that going down into the UV. Not so much on my own behalf, but I have colleagues working with deuterium. And so far, they have been struggling to get hydrogen-loaded hollow core fibers to get high levels of power delivered in the UV regime, which in that case is 370 nanometers. And as you have seen from the result, for instance, at ETH and other nodes, we already now are working towards the integration of waveguides into our fused silica traps. And so if someone wants to work in that area, again, please let me know and extend all of that towards the UV. And with that, I hope I was able to show you that quantum computing is an interesting field. It's a field which is currently rapidly growing, and at least for ion traps, it's also building a lot on top of photonics and photonics know-how. And as we want to scale up these systems, we have to push these capabilities together towards the next level of a few hundred and a few thousand qubits. And with that, I'm done from my side. I'm happily looking forward to questions and discussion.
Thanks a lot, Thomas, for your very clear and inspiring talk. So I'll now go through the most upvoted questions. Let me start with the first one. What are, in your view, the other most promising platforms besides trapped ions and superconducting qubits?
So there are two platforms which are currently heavily pursued. One is photons. So that's, for instance, research by Jeremy O'Brien. Now, previously was in Bristol, now is with Quantum in the US, but also Chanbai Ban in China. So photons have the advantage that, well, it's fast. It's directly integrated into, say, normal semiconductors and chips. The main challenge there is to produce photons, like push-button photon generation of suitable fidelities and of similar specs. And that's a challenge that will likely remain for years. The other strong field, which is pushed a lot now, is Rydberg atoms. The advantage for Rydberg atoms is that they usually can store atoms using optical tweezers. So some of you using spatial light modulators might be familiar with, for instance, the work by Lukin, Bloch, Tillmann, Pfau, and others. And they have the big advantage that already now they can easily load hundreds and even thousands of atoms in 2D arrays. And using Rydberg interaction, they can also build a quantum computer. The main challenge for them is actually that these gate operations so far have been lacking behind in quality. So the gate operations are, let's say, on the order of about 97–98% fidelity, whereas Stefan and I are more used to 99.x. So technologically, you could say the control is a couple of years behind. The big advantage for them is that they can easily generate 100 or 1,000 qubits. Personally, at least midterm, I would argue probably Rydberg atoms is going to take the lead with respect to photons, but on the very long run, we'll have to have the technology from the photonics community to again connect these devices. And I hope that wasn't too long an answer now.
No, thank you very much. So the next question is, the surrounding infrastructure seems to be complex, requires high accuracy, not small and expensive, as it needs a vacuum chamber, ion traps, electromagnetic field, and lasers. How do you see this being shrinked to small, robust, and inexpensive systems?
So what we currently can do is, like, I agree with you partially, but we've been working with Infineon, for instance, on chip development. And students that now visit us with a new design, they essentially come with a bucket with a few hundred traps. It's like they use a normal wafer, you have a few hundred traps on them. We usually need 2 or 3 and the rest gets thrown away. So the production cost of these traps is very, very low. And the next advantage, like what you can do, these things still operate, in contrast to other technologies, operate at room temperature. So we can build these devices, from my point of view, when we get the fiber connection and fiber integration, waveguide integration going, besides having some kind of pump, whether that's a neck or whether we go for something similar, I mean, there is not much holding us back from getting an entire Eintrap-based quantum computer on the size of essentially a smartphone, because it's just fibers. It's a little bit of RF, which is like a couple of like below watts if you have decent resonators, and it still stays at room temperature. You can even take just stainless steel, put it in there, bake it out, and go for that. So at least from my point, there's like nothing stopping us from getting that to work. On the very long run, it depends a little bit on whether you want to go down the path from crisp balance and then have a stack of these units fiber connected, or whether you want to have a larger system. But this, what you could have here, is entirely feasible.
Very good to hear that. So the next question. Do you plan to include integrated photonics in your systems? If yes, what are the most important parameters here?
For the main challenge for us is the wavelength. So we tend to work with down to 400 nanometers lasers, and getting waveguides, single mode and polarization maintaining integrated into our trap designs is challenging. But if whoever wrote that, because I don't manage to see it, please get in contact with me.
Yeah. Okay. Then I just go on with the next question.
Now I found it where it is.
Yes. You're nipping. Now the next question is, what are the main limitations to gate fidelities when controlling ions with laser pulses? Are there limitations from the optical setup? So
the way we currently do it is we really drive the excited state resonantly. And in order to achieve that, we have to have lasers with, and you can infer it indirectly. So the lifetime is a second. So the inverse is a hertz. So the laser has to have a line width of a hertz. This might sound narrow for you. I mean, we've done that repetitive now in Innsbruck. It's essentially not even a PhD thesis and not even a master's thesis anymore. But yeah, this is obviously a challenge. What you can do is you can build Raman-based systems, and in that case, you immediately map RF stability onto the stability of the lasers. This is something where we just recently managed to realize a really nice gate. The performance is not as good yet, but then we can get, again, everything to the size of a shoebox, ideally, to control that. The main challenges are, at the end, it's phase stability, where, again, integration helps a lot. The next problem is intensity stability, where, well, that's mainly technical, and the question, again, of polarization and phases. And other than that, from what we see, gate fidelities of 10 to the minus 4 level are not really, there's no roadblock at the moment.
Thank you. So we have a couple more questions and a few more minutes left. So what is your view on scalability associated with modular designs and associated photonic component level costs that scale with large qubit requirements? This could be considered both for trapped ion quantum computing or photonic quantum computing.
Or Rydberg atoms as well. Yeah, so that's actually how we started. I mean, the idea for us was, look at, again, HPC, learn from the rest of the world. I mean, we've on purpose used the 19-inch rack, not just to make it compatible with installing it with potential customers, but one thing was that we immediately wanted to have a modular approach so that we can replace, let's say, the laser system when there is a new version. We wanted to be able to replace, for instance, we have some routing and beam distribution. Ideally, I would like to have a waveguide there where there's a couple of fibers going in, everything is in the waveguide, nothing can get misaligned anymore, and get that out. For us, it would mean just pull out one box, put the new one in. And that's what we are doing now. And yeah, the next step, at least on our side, but also the Rydberg side, and also photonic quantum computing, whether that's now Jeremy O'Brien with PsiQuantum, Anthony Lang in Bristol, and others. I mean, that's there, and we can do that, and we should do it. So, like, it's as you saw, I guess, from the slides from Jonathan Holm at ETH, this is something that we are currently working on. Like we as ions community.
Okay, thank you very much. So if the lifetime of the optical transition defined the state of the qubit, could this time dependency make the computation very time expensive?
No, that's actually, you want this to be as long as possible. Think about it, something like your laptop. You want to have a picture of your daughter stored, and ideally, if you open the laptop tomorrow, the picture is still the same. So the qubit lifetime should be as long as possible. The storage time of your ions should be as long as possible, because that means how long can you store information. This has not necessarily anything to do with the question how quickly can you manipulate it. If you think about Rydberg physics, which can be implemented both with ions and atoms. So for instance, Markus Henrich in Stockholm was one of the first ones to show Rydberg interaction with trapped ions. You can have coherence times on the order of minutes and more. We can store the ions per se on the order of weeks. I mean, we had one experiment where the barium ion even had a name because we kept it for a month. But on the other side, the gate operations can be manipulated on the time scale of 100 nanoseconds. And that's what you actually want to have. You want to have this ratio of lifetime divided by the gate time should be as large as possible. So you have to push in two directions. Make the lifetime as large as possible while making the gates as fast as possible. And that brings us to new physics and, again, new photonics. Because the Rydberg lasers, for instance, are farther in the UV and need laser pulses with nanosecond control. And that's challenging with an AOM. And yeah, one thing leads to another.
Thank you very much for all your answers. So there's still a couple of questions left, actually, and we're also good in time. So I just continue. That's fine with you. So miniaturized thin film filters, for example, 25 × 25 micrometers, interesting for routing the laser light.
Well, I'd need to know a little bit more what you mean with routing. But let's put it that way. If we can somehow get this thing inside a multi-layer trap, which is based, for instance, on fused silica and so on, very much please let me know. What we're currently trying to figure out, like a typical dimension of our traps is, let's say, rule of thumb, 1 centimeter by 1 centimeter. There are some slots. So yeah, it's actually, that could be something where we, for instance, route light at least into the material and then go on. What we'd also need is micro optics, because at the end you have some facet and you want to have foci on the order. Ideally, what we're doing from the outside with an NA of 0.6, we want to have foci of about 1 micron. I don't believe that this will be possible with normal waveguide integrated approaches, but at least foci on the order of 5 to 10, let's say 10 micron would be good. And so whatever we can do with these thin filters for routing, but also connect it somehow with addressing, that again would be interesting to us.
Thank you. So the next question. Are there any propositions of 2-qubit gates that do not rely on single photon transmission? I understand that single photon coupling in optical setups can only achieve mediocre fidelities.
Okay, yeah, I mean, I'm not sure. So like, it's probably a question of what you consider single photon coupling. So what we like, if you think about it like one color, these gate fidelities, the highest gate fidelities achieved so far were essentially all of them single color and not single photon. That would be a little bit challenging, but yeah, it's all single color because yeah, it's quite easy nowadays to have a laser with a 1 Hz line width. Actually, for some of these setups, the limitation is not so much coming from the laser per se, but from magnetic field and other effects. But you are also right. So people are working on Raman Gates. So there, you essentially do a phase lock between two lasers, generate a 2-photon transition. It works quite well, but actually the long-term fidelity limits seem to be worse on the two photon transitions, because you have to have an excited state to couple, and usually the scattering from this excited state is the main limitation. So you could say I only have to detune farther, and then I'm done. So that's on paper, that's correct. The problem is you have to get the same levels of coupling. You have to increase your laser intensities quite a bit. And for everyone who has done it, you don't want to have watts of UV light in your integrated waveguides floating around. And so the more you can stay on the red and so on, the better it is to circumvent this scattering. So it's not completely clear yet. So just microwave gates are a possible alternative, but these tend to be slow. Two photon transitions tend to have a scattering problem. So single color stuff tends to still be one of the strong candidates.
Okay, thank you. So maybe one last question now. Is there any main challenge or single challenge solution technology which would be a breakthrough in commercializing quantum computing?
Sure. I hope Stefan says the same afterwards. The main problem I would argue for the moment is think about the full stack. We are not talking about just imagine you'd have this laptop in front of you, but you wouldn't have an operation system. Imagine you'd have an operation system, but you have no program where you could have a video conference. So you'd have to have the hardware together with the software, but you shouldn't forget you have to have this use case for an end customer. In order, and you nicely put it there, you said commercialization, you have to have a combo of a hardware plus the software plus a use case for an end user to show some commercial benefit of using the quantum computer. To date, no one has achieved this triangle of like building the hardware with the software and having a use case where you really have a commercial benefit in terms of like there is something that you can rely on and you do it repeatedly and it gives you an advantage compared to any other solution. Even these quantum advantage experiments from Google, so John Martinez and Helmut Neben, as great as it was, I mean, it helped the entire community, and therefore I'm thankful. But there is no, as far as we currently know, no use case. And if you just build something for the sake of having it, but no one can benefit from it, this is really, for me, the next thing we really have to achieve. And I hope the rest agrees.
Okay, thank you so much again. So one thing I quickly want to mention is that this webinar will be recorded and published next week, and that all questions that could not be answered now will be sent afterwards to the attendees that had the questions. So now it's time for Professor Dr. Stefan Philipp, who will talk about quantum computing with superconducting qubits. Stefan Philipp finished his PhD in technical physics at the Technical University of Vienna in 2006. He then joined the Quantum Device Lab at ETH Zurich, where he worked on hybrid cavity QED, geometric phases, quantum optics, and quantum information processing with superconducting circuits. Afterwards, he joined IBM Research, where he first worked at the Watson Research Center in New York, and then moved to the IBM Research Zurich Laboratory, where he became technical leader of the superconducting qubit team, focusing on quantum information processing with superconducting circuits. Since May 2020, he holds a position as full professor in physics at the TU Munich, and is director of the Walter Meissner Institute of the Bavarian Academy of Sciences and Humanities. So welcome, Stefan. We are very excited for your talk.
Thanks a lot, Lisa. Thanks for the nice introduction. Thanks also for joining here, and thanks, Thomas, for covering all ground or some ground already on the way to the quantum computer. And so it's for me now to present some recent developments and capabilities of another platform, which is superconducting qubits. And Thomas has already mentioned that there are several platforms around, and superconducting qubits is definitely one of those which can already show some good results towards the way to the quantum computer. In this setting, in this Photonics World of Photonics webinar, we are entering a different realm now. We are going away from laser light, but more into the photons in the microwave range. So, but I also want to make links, and it's also important to see that we have to see whether we can link these different technologies and there optical photons will play an important role, but I will come back to this later in the talk. So let us recall, what is a quantum computer and why are we interested in that? So we are interested in that because it can solve some type of problems which couldn't be solved otherwise. And that's different categories. We have algebraic algorithms, we have optimization algorithms, but maybe most importantly for the beginning, we have algorithms that allow us to simulate quantum mechanical systems. I will focus here on chemistry, just as an example for what can be done, but there's also material science and other fields of interest where a quantum computer can be useful. And that could be, as Thomas mentioned before, one of the applications that we can have in mind, but we also have to keep in mind that we are not there yet. So, and I want to highlight now what is the current status and what can be done. So, what is it in quantum chemistry? Why is it hard actually? And it's hard because there is electrons, there is many electrons, and the more complex a molecular structure gets, the more electrons there are. So what we have to do is, we want to find a solution to this equation here, which is the Hamiltonian. We want to find the ground state. So we want to solve a certain type of equation, which relates to how many electrons there are and how they are arranged in a molecular structure. The easiest way of thinking, maybe some can remember or can recall, there are physics courses. You have electrons, they like to occupy orbitals, and then you can number these orbitals and arrange them along on the energy axis. And there is different possibilities to arrange these electrons, sitting, for example, in a simple hydrogen electron on the left side or on the right side. And these possibilities you can then count. And a simple way to estimate is that you take how many orbitals you have and how many electrons you have and how to distribute them. And if you do this calculation, it's easy to see that there is an enormous number of possibilities. And that's reflected then in this quantum wave function that describes the system. And for just storing these different possibilities takes so much memory that it's impossible on a classical computers. So that's one way how to see why a quantum computer can be more useful. So it's just, we have to keep track of all these possibilities and find a way actually to describe the system. And here a quantum computer comes in handy. Why? Because if you take now the state space that is spanned by a qubit can be in superposition states. So it can be in zeros and ones, but it can be in 0 and 1 at the same time. So to describe this state, we need for a single qubit 2 coefficients. Say that's 16 bytes if you store it in doubles. But the essential part is now, if we increase the number of qubits, we need, if you have 2 qubits, 4 states, and that's 2 to the power of 2. So that's already 4 coefficients. If you go the next 3 qubits, is 2 to the power of 3, and so on and so forth. So we see now that there is an exponential scaling of the number of coefficients that we need to describe the qubit state. And this exponential scaling is actually quite useful because then we can store the entire wave function of a certain molecule in the qubits. So basically we use a quantum system for describing a quantum system. And if we take now these numbers here and start now looking at where is the critical line where a quantum computer or where a classic computer cannot keep track of it. One finds out that around this 50, 55 qubits or so, it takes an enormous amount of bytes and it's impossible to keep track of this on a classic computers. If you go to 256, for example, it's more than the number of atoms in the universe we would need as coefficients stored on, say, a classical storage drive. So that tells us that using qubits for describing molecular structures and using a quantum computer to compute some properties like the ground state could be useful. And that's seen in this table. For example, for water, it's 10 to the 4 classical bits would be used, we would have to use, but only 14 qubits. And I come back to this only. For caffeine, for example, we would need already 10 to the 48, but 160 qubits would suffice. So the question is then now, and we heard already from Thomas, that we need a device, we need a hardware. We need actually a hardware that realizes these qubits, and there is a few around, And one of them is superconducting qubits. And here, for example, you see, and I want to go now into the details a bit, what is the different components that are used in a superconducting qubit processor. We have a qubit, and we have links between these qubits, which also provides a link to the outside world. That's here a resonating structure, and we'll see that in this resonating structure, or in these transmission lines, they guide microwaves. And these microwaves are used for linking the qubits, but also for controlling the qubits, and can also be used for linking to the outside world. So let's take a step back, go to electronic circuits. You probably all recall that there is capacitors, and there is inductors, and there is resistors as the basic circuits elements. And now we want to make a quantum circuit out of that. So first, we discard a resistor. That's with this cross here, because there shouldn't be any resistance that causes always heat and disturbance and noise. So let's get rid of that. So the simplest element we form is an harmonic LC oscillator with an inductor and a capacitor. In a classical description, we have the electric energy and the magnetic energy, which gives us this Hamiltonian. We can now go ahead and quantize this. Here we just put heads on it, but it means now we are going into a regime where this A is here to describe now single photons, single excitations in this harmonic oscillator. Important here to notice that the structures that we're looking on work in the range of about 5 to 10 gigahertz. So as I said, we're dealing here with microwave photons. And why I'm talking about photons in the context of LC oscillators, because one realization of these photons, of these LC oscillators, is a coplanar waveguide resonator. So how does this look like? This coplanar waveguide resonator is nothing else than we have a center conductor and we have a ground plane, and that's basically a B and C cable, a coax cable, cut in a 2D version of a coax cable. So if we intersect this ground plane here, and I don't find this drawing either, if we intersect this ground plane here and send in microwaves, they will be reflected back and forth by this impedance mismatch, by this coupling, by this capacitor gap. And then a standing wave will form, and these microwave photons that form a standing wave close to this resonance frequency, which is determined by the length of this, can be seen as equivalent to an LC oscillator. So with this, we have photons, and we want to couple then qubits to these photons, to these microwave photons. Remember also that an LC oscillator is a harmonic system. A harmonic system is not useful as a qubit, so we need to add something else to our electronic circuits. And this element that we need is a Josephson junction. It is a nonlinear element. Basically, you can think of, as shown here on the bottom left, as two electrodes, which are separated by a tunnel oxide layer. And this allows now Cooper pairs. We have superconductors, so electrons come always in pairs. It allows these Cooper pairs to hop from one electrode to the other electrode. And this you can, in a simple picture, already visualize as being the states of the qubit. One Cooper pair here or there would resemble the 0 and 1 of a qubit. In a slightly different picture, you can see this as an anharmonic LC oscillator. We have an inductance, which depends on the energy stored. So we have a nonlinearity in here. And this nonlinearity provides us now with a potential where we have the first two energy levels are separated with a difference energy to the other energy levels. So we can separate the lowest energy levels and use them as a qubit. On the top right, you see how this Josephson junction looks like in reality. The size of that is this first qubit structure is about 500 microns. And what you see then on the right picture, you see this junction area, and that's about 100 nanometer in dimension. We can also add some control knobs to tune the frequency, and that gives us the possibility to control these qubits, control the frequency, and couple them to resonators. And that's what relies on that is the interaction of matter and light, which one knows from from optical frequencies as cavity QED, cavity quantum electrodynamics, where there's strong coupling by some atomic structure, by some qubit structure, to the optical light field. And here, instead of using optics in a cavity, we have microwave photons in the transmission line, and we couple artificial atoms, we couple the qubits to these microwave fields. So the advantage here is that we get strong coupling, so we can couple these qubits to single photons in the cavity because of the small size of the structure, also because the photon lives long, relatively long, they live for milliseconds in this resonating structure, and the artificial atom is huge. So I said it's about 500 microns in size, so we have a huge dipole moment and a relatively long coherence time. And that allows us now to couple systems at the single photon level. That's a picture of one of the first experiments where this happened, showing that one can do quantum electrodynamics experiments with single photons and show that was basically the starting point of current superconducting qubit processors. What is important, and I mentioned this, is that these microwaves also provide a link to the outside world. So it's not only that we can couple the qubits to this resonator and using this for linking them together, but we can also think of emitting photons. We can use traveling waves. We can use basically propagating photons and send them to different nodes. And that's a recent picture in one of the recent publications here, how one could imagine such a network built out of quantum computers, repeaters, sensors, and what's needed is these links in between. And there is now, from the superconducting qubit point of view, there is different directions to follow. So one way could be that one thinks we use directly the microwave links. Clearly, we have to find coax cables we need because we use superconducting elements. We need to find ways to use cryogenic links. But for small distances, that's now currently what's also done in the lab. One uses connections between cryostats here and sends photon around. There's methods how to shape these photons so that you can emit them with high probability on one end and receive them with high probability on the other end. On the other side, one could also think about, what about conversion? Can we go from the microwave to the optical domain and use then optical photons for converting, for converting microwave photons into the optical domain and then use this for communication purposes? And there is ongoing work which is extremely interesting and different technology used for this or pursued for that. For example, one way is to use electro-optic material, where you change the electric constant of this material and modulate then the microwaves onto the optical light. There is other options using optomechanical systems, where you have a cavity, an optical cavity coupled to a mirror, which in turn couples to the mechanics, and this mechanics then modulates the frequency of a microwave resonator. So with this two-stage process, one can then couple the optical field to the microwave field. And that's current research is going in this direction. The challenge here is that there is low conversion efficiencies. One has to keep in mind that one has to cover about 5 orders of magnitude in frequency. So these low conversion efficiencies, that's a challenge. And also the bandwidth is a challenge. We want to have some conversion which works in a broad band, and getting this to work is currently ongoing research. So where else do we use photons? We use them, as I said, for controlling the qubits, and that's pretty simple. We send in microwave signals, they couple capacitively to these qubits, and with this we can prepare these superposition states of single qubits. Note the different pulse, the typical pulse duration that we are looking in is somewhere around the 10 to 50 nanosecond. And the fidelities that one gets nowadays in 99.9 or 99.99, so in this range. Here it's also interesting because now we have microwave control, and in this frequency range, we can readily think of how to make these pulses shorter and how to make these pulses better. And what we are currently pursuing is shaping these microwave pulses, shaping the envelope and optimizing these pulse parameters, so to get even shorter pulses with still high fidelity. So here it's shown that we are using a piecewise constant to approximate the Gaussian pulse, and by tuning, by optimizing the different parameters, so that's shown here in these different iterations, we change the shape of these pulses. We get to different shapes which are adapted to the system at hand. And with this, we find that we can increase the fidelity. So what's shown here is the gate fidelity on the y-axis as a function of pulse length. And what we demonstrated, that by using this piecewise constant, so these red dots, we can go to even shorter pulse length and at constant gate fidelity. And that's one way to pursue and extending this to different gates, to making the gates shorter, because as Thomas already mentioned, it's this ratio of how much coherence time do we have available to how many gates can be accomplished within this time. So making this gate shorter and better controlled is one way to fit in more gates. There is also, microwaves are used for 2-qubit gates. Here it's just, I don't want to go into the details. We use for 2 qubits a coupling via the bus, and by shining in microwaves at a certain frequency, we can control now the state of this qubit 2 as a function of the qubit 1. The typical pulse duration are a bit longer than in the single qubit gates. It's about 50 to 150 nanoseconds, and the typical gate fidelities are a bit lower, but has recently tremendously improved, so that we are also here in the range of 99.5% for the 2-qubit gates. So putting this all together, we have the basic elements of a superconducting qubit processor, having these transmon type qubits, living about 70 microseconds or even longer, 100 microseconds, in the range of 10 to 100 nanosecond gate times, and having these microwave resonators for as a bus for coupling these qubits, but also for reading out the qubits. How does this look like? We have superconducting qubits. This all goes into a dilution cryostat. So what you see here on the right side, there is different stages going from room temperature to 40 Kelvin, 3 Kelvin, about 100 millikelvin, and down to base temperature, which is 20 millikelvin. So that's minus 273.14 degrees Celsius. So that's basically because we have first superconductors, and the second thing is we want to avoid any thermal radiation at the position of the qubits. But this can reliably done. So we cool these superconducting chips down to this 10 millikelvin, put them here shielded against all thermal radiations and against outer environmental influences, and control them using microwave electronics. That's how this setup looks like in the lab, here taken at the IBM lab. That's what you see here is a vacuum can, so it's a huge thermos can with different shields. And what you see here in this figure on the left side, so that's the interior with different shields against magnetic fields or against electric fields. So what is the state of the art? We have heard that we have, so to say, quantum computers or quantum computer prototypes that can reach up to more than 50 qubits. I listed here Google's machine, IBM's machine, and also the AQT and IonQ, the trapped ion machine. So that's basically the most advanced at the moment. And there is many more in development. For example, there's a European effort. Now we're also starting a German effort in getting this to better and better performance with these technologies. Thomas already mentioned there is first signatures of quantum advantage has been demonstrated. It's debatable how useful this is, but that's basically sets what can be done. But it's also clear that there is many challenges ahead. And the next milestone, we also heard this, is coming up with a practical quantum algorithm. Another milestone is coming up with a logical qubit, which would give some protection against noise and errors. I want to mention here one of the, so IBM, for example, it's usable, so everybody can try it out, and there is a fleet of different quantum computers available where one can get already first insights on how this would work, not with 1 or 2 qubits, but as many as here, for example, I see 15 qubits, but more of them are available in the different settings that can be used. Now, what we want to have at the end is a universal quantum computer. And the problem with that is it could run all the algorithms that we could dream of, but the problem with that is that there is errors and noise. We heard this now several times. So a way out is to find some correction schemes that would give us the means to correct for errors without destroying this quantum information on the chip. In a simple way, we would need something where we have, instead of just a single bit, like this 0 here, we would encode this in many zeros. And if one of them fails, then we just have to identify that there is an error. In the same way, we could encode the 1. And if we find a way how to do this, and there is known ways how to do this, we could build a stack where we could run all these quantum algorithms on logical qubits. Now, that's difficult. And so we are close to getting first results on logical qubits nowadays. But it is still the case that, okay, that doesn't work, where we have to basically get rid of all these layers in between here, but use quantum algorithms that can be run on the physical qubits. And just briefly, I want to mention that there is one way how this is done at the moment, which uses what I mentioned in the beginning, which uses this power of a quantum computer to store states and to store information in these coefficients of a qubits. So it's known as variational method, and how it works is that it uses a quantum classical system that prepares states on the quantum coprocessor that's seen on the left here. We prepare the states that is the right state that minimizes, for example, the energy of the qubit, so to find, for example, the molecular ground state. So we define a cost function, we prepare this quantum state here, and we then minimize this cost function by using the classical optimization regime, the classical optimization algorithm. So by this, we choose different parameters to prepare this state, and we stop when we have found the minimum of this, and this gives us the quantum state, and it gives us the minimum of this energy function, for example, the ground state of the molecule. The takeaway message is we rely on having a classic computer, powerful for optimizing parameters, and a quantum coprocessor. And this works out pretty neatly. We see this in first experimental realizations of simple molecular ground states, for example, hydrogen or lithium hydrogen, but also hydrogen chains can be simulated. And what you see here is the binding energy. And these dots is the experimental results on quantum processors. And you see that these are already pretty close to the expected binding energy value as a function here of the interatomic distance. And getting closer and closer to these values can be seen as a benchmark of a quantum computer as well. So that's where we stand. You might say, okay, that can be done on laptops, but one also has to see that the technology that goes into classical computers nowadays looks back at the long history, and so the competition is quite hard. And we can also say that it takes probably more than just a little bit of paper and writing to calculate the ground state energy of lithium hydrogen. So I would say that also quantum computers are already quite powerful in some tasks, but it's clear that it will keep us busy a while to actually extend the possibilities and go to more complex molecules. Just briefly to mention, it's not only ground state of molecules, we can also calculate excited state, but that's now ongoing research, what can be done, what algorithms are useful, and how they map onto the quantum computer, into the qubit technology. And so as Thomas mentioned, We are trying to build quantum systems that are based on physics to solve problems that are otherwise intractable. And it has to be a mix of both optimizing the algorithms on one side and increasing the capabilities of the hardware, improving the hardware, so that we find a match, so that we can go towards this universal quantum computer, where we know that we get a speed up, but we using basically what we have now in using hardware efficient apps right now in this medium scale picture, where we don't have full error correction, but still find a practical algorithm that can help us already quite right now to get some useful applications out of a quantum computer. The challenges are there. We need to work on scalability, the control and coherence of large systems, but it's the problem that we need to solve is intriguing enough so that I think there is lots of motivation to go along this track and to eventually end up with this universal quantum computer. With this, I want to finish and thank you for your attention.
Thank you, Stefan, for this really great and enlightening talk. Again, I will go through the most upvoted questions now. So the first one is, do you see superconducting quantum computing to be used in specialized applications, unlike commercial applications, or do you see a future without cryogenic cooling?
So there is two answers to this question. So first, the special application, that's what's holds for any quantum computer right now, because we don't believe at the moment, at least, that it will replace any laptop computer for running your PowerPoint presentations. So it will be specific applications where a quantum computer is more useful than a classical computers. And the way, and that's also not only in quantum computing, but also in classical computing, the way how it's run at the moment, that's cloud-based services. And with these cloud-based services, you don't rely on having this basically standing on your table. There is no need at the moment. The other answer to this question is that one has technology available that can cool down the superconducting qubits at the moment, but as technology is also, one can think of improving this technology in getting also these cryostats smaller and smaller, and work on that to improve basically also on the usability, on the practical usability, and on the deployability of these cryostats.
Thank you. So the next question is about the qubits need to be similar to be connected, because at the same time you also need them to be different so that the microwaves only manipulate the desired qubits. So how do you think this challenge of frequency crowding with respect to the growing number of qubits can be solved?
That's indeed an issue. Frequency crowding is an issue, which can be solved actually in design, and there we need to solve some of the fabrication issues. So at the moment we have qubits that we design to be identical, and by having fabrication which is reliable only at the level of 1% or so, or 2% or so, we get differences in frequency. That makes it more difficult to design. But it's also there, that's not a hard stop to scaling up, but there needs to be constant improvement in fabrication, and there is many promising results along these lines, so that you can then really design the qubits as you wish, to the frequencies that you wish, and also use different qubit designs that are more like a qubit than an anharmonic oscillator, to avoid this frequency crowding and to avoid addressing different frequencies. So there is basically in fabrication and in design, there is lots of room for improvements to scale these devices up.
Thank you. So the next question is, how do you maintain mixing coefficients of the qubits? Molecular problems need essential variations of the mixing coefficients. In the calculations on the molecules, the valent electrons play an essential role, but the rest of the electrons have to be also accounted in the higher order correlations that have relatively small impact, but are very important for finite precision of all, as all spectroscopists know.
Yeah, I think without knowing the details of this answer, I think the general answer to this is that clearly we have to make use of all the approximation methods that are used in quantum chemistry on the classical side, also for a quantum computer. And that's ongoing research done in different places, also, for example, in IBM, where I worked before, in looking of what can a quantum computer do, what is the best way to deal with, to represent this electronic wave function on a quantum computer, which approximations to make, and how to get reliable to the results that I would that I want to have at the end.
Thanks. So there's still a few more questions coming. How would room temperature superconducting materials affect the qubit setup? Could you avoid dilution refrigerators?
Yeah, that's an interesting thought. One can think along these lines. But only having high temperature superconductors won't help, because I didn't go into the details of that. We also know that room temperature radiation, it's basically when you turn on a microwave, then it's just heating up things. So we are in a frequency range where this causes qubits to be excited. So if we stick to this frequency of the 5 to 10 gigahertz, we will suffer from thermal radiation exciting these qubits in an unwanted way. So by going to high temperature superconductors and trying to operate at room temperatures, we also have to figure out whether we make higher frequency qubits, and how this then goes together. That's an open question. At the moment, it's lots of material science would go in there.
Thank you. Can you estimate how the quantum volume of two linked processors would scale using quantum links? Is it the combined volume, or does the single link diminish the combined volume?
I don't know the exact answer to that. There is works on that, how distributed quantum computing would help, and taking into account also what is the efficiency of how these links work. And basically, because on the quantum computer, you always have the benchmark that your single 2-qubit gates, or your qubit gates in general, have a certain high fidelity, and you would have to have the same requirements for these links. And then you have to take into account how efficient these links can be and how many qubits you can link. So there's certainly a degrading of the quantum volume, but I can't give a quantitative answer to that.
Okay, but thanks a lot. So what are the main challenges that this platform will need to face in the next 3 to 5 years?
The main challenge I think I've discussed is definitely on the design side, getting the microwave, also the classical crosstalk into control, getting the simulation, getting basically the designs to work reliable also for larger systems. Another point is in fabrication. There is always room for more coherence. So, and that's definitely a materials question, but also a fabrication question, but also a reproducibility question. As mentioned before, for example, this Josephson junction, we can get to an accuracy which is pretty good, but which is still not enough to basically be on spot to the frequency that we like to have. So that's one of these challenges among different others. Like there is also challenges in the peripheral components. We rely, for example, on circulators and isolators, and they are bulky. So that is one of the solvable bottlenecks, but still somebody needs to work on that. And that's probably one of the challenges, is also then bringing the different know-how together from the different fields and letting the different people bring in their ideas how to form this complete stack of the vertical system, as also Thomas mentioned before. It's not only in the superconducting platform that there is challenges, but getting this all work together. That's probably the main challenge.
Thank you. Next question is, do you see a possibility for Germany and Europe to take the lead in developing a quantum computer based on superconducting qubits? If yes, what is a realistic timeline for catching up with IBM and other leaders in the field?
I don't want to answer on the timeline. That's always hard because nobody wants to speak about timelines for quantum computers in general. So that's definitely, I don't want to do that. I still think that maybe we are not in the very beginnings of quantum computers, but there's still a long way to go. And so it's still one should actually pursue this here in Germany and Europe, and there is first attempt, what means attempt, there is first programs in doing this. It's definitely a challenge to keep up, but I think there is also a lot of opportunities following different directions within platforms, for example, with different directions in superconducting qubits, but also for different platforms. So I think this is still an open question, which platform and also which approach will win. So the answer is a definite yes. And so yes, we should pursue this.
Thank you. Happy to hear. So last question. Is there a way to build a microwave to optical link by using frequency comms or optical cavities with free spectral range in the 5 to 10 gigahertz?
As far as I know, there is also work in that direction. But one needs to figure out what is the details and what is the technical implementation of this, and where is the losses coming from, what determines the line width, and what determines the coupling factors, so that one come to a good estimate of how this cooperativities, basically how the efficiency for this conversion then works out.
Okay, well, thank you so much again. And with this, I'd like to thank everyone for your participation in this first webinar, and especially again our two speakers, Thomas Mons and Stefan Philipp, for their insightful, illustrative, and clear explanations about the foundations of quantum computing and the importance of different hardware platforms on this exciting quantum computing journey. We look forward to the second webinar, whose date is not confirmed yet, but stay tuned, it will be following soon. I hope you all enjoyed this webinar, and in order to improve our LASER World of Photonics talk series, we would be very pleased about receiving any feedback. You can find the link for the survey in the chat, and it will also be shared in a separate email. If you want to be informed about future activities, you can follow the LASER World of Photonics Twitter account. And if you want to stay updated about quantum computing in Europe, you can join our European Quantum Computing Applications community group on LinkedIn. On behalf of Messe Munich and IBM Research Europe as co-organizer, I would like to close this session. Thank you, stay healthy, and all the best from Switzerland. We hope to see you all soon for the next webinar. Bye!